Hello everyone, my name is Jose Leal and I am a member of the Edge DevTools team. In this session, my friend Rob and I want to talk to you about some new features for performance and memory analysis. We will start with an overview of the memory tool, then talk about a new feature called detached elements. We're going to show you how to unminify performance profiles, and then we're going to go over some new ways that you can integrate source maps to improve the debugging experience of production code. This is the memory tool. I bet most of you are already familiar with it. But just as a refresher, let's go through an overview of what it does. The memory tool allows a user to take a snapshot of whatever is happening inside an instance of V8, which is the JavaScript engine of the browser. Users can explore the snapshot and see all the allocated objects and what is causing them to stay in memory. Here, I have an instance of DevTools for a GitHub page that I want to inspect. When I click on the button Take a Snapshot, I'm sending a command via CDP that returns a file with all the information about memory. The tool reads this file and reconstructs the memory graph. While doing so, it creates a list of aggregates that group elements by class name, and it calculates the retained sizes. You can search for a specific kind of object or select an instance to find more details about what is keeping it in memory. In other words, its retainers. Debugging memory issues can be time-consuming, and sometimes you may need help from one of your peers. If you want somebody else to take a look, DevTools allows you to save the snapshot, so you can share it with another person who can later load it in their machines and explore it. If you were to open this file in your IDE, you will see a lot of numbers. It's kind of hard to read. So you may be wondering what is going on inside. The information in this file represents a graph, full of nodes and edges. But this graph needs to be serialized, so it can be easily transported between the browser and DevTools. To reconstruct this file back into a graph, we need to understand its format or schema. As it turns out, this file is just a giant JSON. So if you rename it and then open it with your IDE of preference, you can format it to see the structure. Here, I am using VS Code and pressing Shift-Alt-F to auto-format it. The information stored under nodes and edges are mostly numbers, and each entry is an index to another node or string that will be used to form the relationships between them. The schema is stored under metadata, and it tells us what each index means and what its type is. For example, if the index points to a string and it's meant to represent the name of a node, or if the index points to a second node and is meant to represent a relationship. The memory tool understands all of this, and that's how it processes the file and creates the summary view that you see. Since we're in the topic of memory, let's talk about retainers. What is a retainer chain? It is a set of references between objects that prevents the garbage collector from removing a specific element from memory. Consider the code snippet below. I declare a class called foo. Then I create a new property A on the global window, where I add an object. And this object in turn has another property called B, which refers to the new instance of foo. So in this case, foo is being retained by a chain AB coming all the way from window. So then if I'm wondering, how many objects of this class foo exist in this point in time? What I can do is I can take a snapshot and use the class filter on top to search for foo. I do this and I find one object. If I click on it to inspect it, I see that the retainers appear at the bottom, and they confirm my mental model because they show me that foo is being referenced by an object via a property called B, and then that object is in turn referenced by a property A coming from window. So now I know that if I want to allow GC to remove foo from memory, first I need to delete the connection B. So now that we have finished a refresher of memory and retainers, let's talk about detached elements. In the past few years, there has been a migration converting desktop apps to PWAs, web views, and other kinds of web apps. And with that, there has been an increased interest in making sure that they run fast and don't consume a lot of resources. A source of potential memory problems comes from detached DOM elements, which happen when objects are removed from the DOM but are still retaining memory by JavaScript. Historically, they have not been a big issue for small web apps. But now that we have complex single-page apps or just web apps that rely on having long-running sessions, it's very common for this problem to grow. Let's see an example. In this demo site, we're simulating a messaging app that has 3 chat rooms. We have opened DevTools to inspect it. We're going to send a couple of messages in room 1. As you can see in the Elements panel in DevTools, these messages are attached to the div element with the class chat. Now we're going to switch to room 2, and this action triggers JavaScript code that removes those messages from the div, but keeps a reference to them in a variable. These elements will be now detached from the DOM tree, so you won't be able to see them, but the script engine still knows about them. In this scenario, this is a good thing, because that way, when the user selects room 1 again, we can just reattach those elements back into the DOM instead of having to recreate them from scratch. This is a very simplified example, but you can imagine how more complex web apps will have scenarios that create and remove elements but leave unwanted references behind. Now that we know what detached elements are, let's talk about the new tool. Previously, you could see the detached elements in DevTools by taking a heap snapshot. Unfortunately, this process can take quite a bit of time, especially for bigger web apps. And finding objects this way disrupted the workflow of debugging. We needed a tool that was more specific and could query detached elements a bit faster. This tool has 3 main actions, which you can access in the toolbar. A button to refresh the list of current elements, a button to trigger garbage collection, and a button to analyze. Let's see it in action. We're back in our demo site, and we repeat the scenario from before. We start by sending messages in room 1 and switching to room 2. Remember how we used JavaScript to remove those elements from the DOM but keep them in a variable? If I click the refresh button, the view shows me a list with all the DOM elements that are still referenced in memory. I can expand those elements to verify they match the structures that I was expecting to see, and I can tell that they persist even after a garbage collection. I want to know what is keeping them alive, so I click the Analyze button. This takes a memory snapshot behind the scenes and updates the view with links using their object IDs. If I click on the object ID, it takes me directly to the retainer panel in Memory tool, showing the chain going all the way up the window. We think this workflow will speed things up and save devs a lot of time. We're excited for you to try it and leave us some feedback. As you can see, the retainers view is very important when fixing memory leaks, since you need to find out what references to remove so that GC can clean your objects from memory. While investigating some memory leaks in our own projects, our friend Seth found and fixed several bugs in V8 that made it very difficult to make progress on memory investigations, because they cause the retainers view to show incorrect information. For example, in this before and after shown on the slide, 2 out of the 4 retainers were incorrect. These fixes were made in Chromium, so now all browsers can benefit from it. These bug fixes were great to reduce visual complexity, and to keep working on that, we also introduced filters. The filter in the retainers view allows you to remove cycles, which were previously shown but grayed out. Same for objects in general. The filter on the aggregates panel allows you to select different types, so you only see a subset of the objects at a time. Here, I'm just selecting arrays and strings. Okay, this wraps up the latest features for Memory tool. Now, let's talk about another powerful tool in your debugging arsenal: performance. This tool is helpful to record different runtime metrics while you go through a scenario, and one of its most powerful features is the ability to zoom into a particular time when an interesting event happened, and then read the call stacks, which looks something like this. But what happens if you record in a production environment? Well, most apps that have been deployed into production have been bundled and minified, which makes the function names in the call stacks very hard to read. Wouldn't it be nice if you as a developer could go straight into production to the site where your customer is reporting an error, profile it, and immediately unminify it right there in DevTools, without having to set up a local environment that matches that exact version? Well, as of Edge 99, we added this Unminify button on the toolbar, which automatically fetches your source maps and applies them to the profile to reveal the real function names. So, if you already publish your source maps publicly, you can use this feature right away, and it will transform your view from something like what you see on the left to human-readable function names like you see on the right. To talk more about how you can get this enhanced debugging experience, if you don't want to publish your source maps publicly, I want to introduce you to my friend Rob.
Thanks, Jose. Hi, everyone. I'm Rob. I'm also an engineer on the DevTools team. I want to talk to you a bit about a problem or a series of problems that we found in Microsoft about our web properties, and we think that you might also run into them as well. You see, a lot of our applications run on JavaScript and HTML. Office has their web versions. Teams runs in Electron and WebView 2. Even Edge DevTools is written in TypeScript and runs in the browser. We can do our best to figure out and debug in our normal dev loop, but when we scale up to millions of customers, we find new problems and performance issues that we just can't handle. So we have to worry about what do we do when we're developing and fixing things in production? How do we get meaningful results? And the main tool we use now for doing that is source maps. Now, why might you care about source maps? Well, are you using TypeScript? Are you using a bundler like Webpack or Rollup? Do you have a bunch of vendor libraries that you factor into your application? Well, what do you do about debugging something like this in production? What if you're having a performance problem? How do you handle the fact that performance is usually slightly different in terms of characteristics when you're in production because of things like minification? So we will use source maps for that. Now, often we don't want our source code to go public, and the best source maps, the most robust ones, do contain source code. Most businesses don't like to publish their source code publicly, though, not because we don't like open source, but often because those things contain our secret sauce, the things that help us be competitive. We don't want those things to be trivially copied. Now, if you're using DevTools, you can set up a workspace, and this is a pattern that you might see, that you download the source maps for a particular version of your files and configure your workspace so that it can load that. But this can be very challenging, particularly because you have to get the correct version so that the files match whatever's on your production website, and this starts to become challenging. Another one, and a notable team inside of Microsoft, although I'm not going to give it away who did it, they set up their production environment to have source mapping URL comments that pointed to a non-public location, and this happened to be IP address restricted. However, the problem is with that, when COVID-19 hit, they weren't at their desks in Redmond anymore, and so all of a sudden they weren't able to access this. So how do we work around this problem? The answer is Azure DevOps. And as of Edge 99, DevTools has been able to connect to and talk to Azure DevOps Symbol Server. It's a secure, cloud-based mechanism, one that's functionally equivalent to those internal symbol server, the internal symbol server tool that maybe you got on an MSDN disk in the early 2000s. It's a generally easy opt-in, requires usually just adding a Webpack plugin or something functionally equivalent as part of your CI build system, and we're actually going to see that happen. Okay, so we're going to begin this demo by showing you the demo property. So this is an application that's based on fast.design that our colleagues in the fast team have chosen to allow us to demo. I chose this one because it is very well minified, so and it's also pretty nicely interactive. So if you take a quick look here, if you're interested in the fast components, they're web components that you can use that we use throughout Microsoft, so you should definitely check that out. Like I said, their website is fast.design. So briefly, I'm going to launch DevTools here, and one of the things that you can see is that all of the JavaScript is very well minified. So it's not particularly easy to parse through. Most of it is just rendered HTML or pre-rendered HTML. And even if I pretty print, the function names have been changed. It's hard to navigate. So we're going to go ahead and now connect this into or load this up into VS Code. You can see that our JavaScript files are, like I said, they're very well minified. So they use Webpack here. Now I've adapted their source code a little bit to not produce source maps. You can see that the source mapping URL comment is omitted from the JavaScript files, but in this particular case, I'm producing source maps. This is the hidden source map property. I don't believe that they produce source maps as part of their normal build. Now I'm going to fast forward by a step just to show you what I've done here, and I've added one file. This is the Webpack 4 version of the symbols plugin that we have on our documentation. And what this does is it basically goes through, and for each JavaScript file that's produced during compilation, it will load it up as a buffer, calculate the hash of it, and then also load the source map as via UTF-8, parse it as JSON, and then append the source map as this property X Microsoft symbol client key. This will then be written to the source map contents, and that will be rewritten back to the output file. Then we instantiate this plugin as part of the webpack.prod.js configuration. We require it here, and then we add it to the end of the plugins list. It's important that it goes at the end because it needs to get the final built version of the JavaScript file, because that's what the hash is going to be running, or the hash is going to be computed for at runtime. So here, we'll now push this, we'll do a build, and in fact we can run build webpack because we don't need to rerun the rollup component. So while this goes, I'll take you through the output, and maybe we can see how it looks live. What I think is interesting here is that you can see that we don't have that property. It's going to be added, and so for the most part you don't need to worry about what's actually happening here, but here you go. So this property has been added, and as you can see it's a hash that's been computed, and in fact this is also going to be true in the vendors.js map. You can see that it's been added here at the end. Now still, we have not touched the JavaScript files, and again, that's important. They still don't have the source mapping URL property. So let's get ready to push this up and kick off a new build to deploy to our website. Okay, so here I am editing my pipeline for the website, and one of the things that we're going to do now is add the index sources and publish symbols task. Now this has to run on Windows. I believe that the tool itself can run on .NET Core, but we'll look for this. So it's index sources and publish symbols. And what you'll see here is that we need to do a few modifications. First, because my specific tool is building to a subdirectory, we're going to copy that and paste it into the path to symbols folder. We'll grab that and paste it in. Now we'll go next to the search pattern. By default, publish symbols publishes PDBs. We don't want that. We also don't want index sources. That comes along for free with source maps. Now we do want to pick symbol server type, just the one in this organization, because that will give us this next item, symbol file formats to publish. We want to select JavaScript-based source maps. We don't want PDBs going up. So that will add this to the publish task, or to the pipeline task, I should say, or the pipeline. And now we can save and commit this to the branch, and that will kick off a build. We'll be back after the build is completed. Okay, so we're finally ready to demo how this works end to end. So I refreshed my site, and you can see that I still don't have source maps, and that's because I haven't configured Edge to load the source maps from Symbol Server yet. So we go back to Azure DevOps and click on our user preferences, open our personal access tokens settings. You can see I don't have any, so we're going to create a new one here. Give it a name, something that will help you remember what it's for. In this case, we're using demo. You can set an expiration if you want, and then click down on Show All Scopes and scroll down to where it says Symbols. You want to opt into Read and then create the token, and this will give you a token that can only be copied one time. So let's copy that and go back to our application. Now I'm going to launch settings by pressing F1. And you can see I go to Symbol Server and type in your Azure DevOps organization, in my case it was my name, and paste your personal access token here. You'll get a prompt to reload DevTools. And there it is. And as you can see, after a second or two, it actually provides us with the source code that's loaded. If I press escape to launch the drawer, you can see I've got a source maps monitor tool that indicates that our source files were loaded from Symbol Server. And in fact, if I want to set a breakpoint in a menu item, I can press Control P to launch the file picker and go to menu item. Let's find code for maybe when we handle a click. Here we go. So let's set a breakpoint in here and click on menu item. And sure enough, we had a breakpoint. So this is it. Secure source level production debugging using source maps in production. So you might be asking, how does this all work? Well, at runtime, Edge calculates, Edge has access to the source code of your application, right? Because it's written in JavaScript. And by source code in this case, I mean the compiled code that's running in the browser. Edge uses this information to compute a hash, and that hash corresponds to the same hash that you computed as part of, or that we computed as part of the Webpack plugin, and which we added to the source map. This results in the construction of a URL that maps to something on our symbol server process, and so we're able to request the corresponding URL and publish or access the information that we need to load the source map at runtime. So that was really good. That was we've seen how to do debugging in production using source maps, but what about if we have other problems like performance? What else can we do? So as of Edge 101, we were able to also embed this information into the performance profiles. So what does that mean? Well, for the most part, performance profiling, as long as you have source maps, works great, as long as you're analyzing the performance problem right now. But if you have to export it or look at it later, things become a little bit more complicated. Chromium-based browsers have for a long time had this issue where if your source code, the site doesn't line up, or if you have to log in as a different user, or if scripts load in a different order, then they'll link you to the wrong place. Now, as part of solving this problem, we have solved that problem for the most part. I don't want to say we've gotten everything. It's actually surprisingly complicated to handle all of that. But a big part of what we have solved is this area where if you load a profile that's been exported and you come back to it, it'll work. So what's interesting here is that when you export a profile trace, then you are able to automatically resolve that information from Symbol Server. So here you can see that I've loaded up Edge Surf, and I've reconfigured my DevTools to connect to the Microsoft Azure DevOps instance so that we can see Edge source code. If you haven't checked out Edge Surf, you should do so. It's a clone of SkiFree from the Windows 3.1 days. But here, I'm going to begin capturing a performance trace, and you'll see that we can dig into the original source code. So here we go. So now I'll begin playing a little bit. It's a little slow, but that's all right. So we'll pause, stop profiling, and as it processes, you can see I can zoom in on a particular graph in the list, and I can click on an area, and I can go directly to the source code that is related to it. Now, that's to be expected because we're looking at it with source maps already loaded, but what if it's not? So here I'm on just the new tab page, and I'm going to import a performance trace that I took a little while ago, and here I can zoom in, and you can see that just like before, I can look exactly at my original source code. So we have production level debugging, source code level debugging and performance analysis in production without having to worry about finding all of our source code and mapping it back ourselves. Okay, so what's next? It turns out source maps really haven't been updated in about 10 years, and so there are some advances that we want to take advantage of, particularly around things like stack unwinding and variable aliasing. Some minifiers are able to do inlining of stack frames. Others are where like you might have a function named T because it got minified. And so these kinds of things are really challenging to work through. So we believe that there's a lot of value to be had there. We're also looking at ways that this can be improved by, like, for example, integration with the Unminify tool that you saw as part of Jose's presentation, as well as improved integration with the memory tool. So with that, we want to ask you, please leave us your feedback and visit and give us feedback at aka.ms/devtoolsfeedback. This will take you to our GitHub where we can interact with you. We want to hear from you. So please do leave us feedback and look at our roadmaps, and we'll go from there. Thank you very much for attending our talk. Good luck tracking down those production problems. Good luck tracking down those memory leaks. And please continue to help us improve the product by talking with us. Thanks very much, everybody. Bye-bye.